Hi, and welcome everyone to this session about Kubernetes access control. Today, that was the one. Hopefully you're going to have a good time following some of the recent developments within Kubernetes access control, some new methodologies you can use. I'm Lucas, working at Upbound as a staff software engineer, and previously I've been contributing to Kubernetes for quite a while, doing different things.
And I'm Micah Hausler. I'm a principal engineer at AWS. I work on Kubernetes security and container security. I also volunteer upstream. I'm on the Kubernetes Security Response Committee, as well as one of the co-chairs of SIGAUTH.
Cool. So let's kick us off. We're going to start by an introduction to Kubernetes access control, then look at the most widely deployed method today, which is RBAC, role-based access control, and a couple of tools that could be useful for managing that. And then we're going to look at, in the second half, a new Kubernetes enhancement proposal, or KEP for short, which, or a couple actually, which kind of provide more finer-grained alternatives to the existing stuff. So in an authorization system, you have kind of conflicting requirements. You want it to be expressive, but on the other hand, it has to be fast, it has to be safe to execute, and also ideally analyzable, so you can kind of know what's going on. And these are, well, at odds with each other. So designing this is a delicate balance. On top of all of this, you need to make sure that it's actually correct, whatever you're designing and implementing. So on a kind of high-level overview, RBAC is fast, safe, and analyzable, but not as expressive. Then we have another method that we'll cover in a bit, which is called validating admission policy, which is way more expressive, but not as easy to, not as fast and safe and so on. And then if you need even more expressivity, you can do webhooks. So you can just tell the Kube API server to just ask this thing for whether it's allowed or denied. But then we can't analyze it. We can't know what this webhook is doing. And it's also kind of, can be prone to failures and stuff like that during runtime. So today we're going to look at, so is there something in the middle that we could do where we kind of preserve some of the advantages and balance these trade-offs.
So when you make a Kubernetes request, whether you're using kubectl or kind of any other client of Kubernetes, there's a whole path that goes through the API server. This diagram here is not even everything. No. This is just some of the possible states on kind of how a API request can be evaluated. In red here, you can kind of see the bad cases where the client maybe made an error or something. But then there's all kinds of other states here where you're calling out to webhooks for authentication potentially, or authorization. You're evaluating out of state or out of memory policies that are tied to state potentially. You're decorating the request with user information, and this is all again happening kind of in the API server.
Yeah, and it continues.
And it continues as well. So we even, if we want to go a little deeper into the kind of authorization part, there's or past the authorization part, there's admission control. There's all these parts of decoding the payload. So this is really just to kind of illustrate, without getting too deep into it, there's a lot going on in the API server every time any client makes a request. You have mutating and validating admission, and then you actually have to also go to etcd, to the database, to get your response.
Yeah. Next, we'll look at a little bit more simplified picture. To keep it,
Yeah, so for kind of a mental model, we'll have, when you do a write request, you first are just gonna really authenticate. So this is, if you're used to using certificate-based auth, CA-based auth, or OIDC, or potentially some cloud-specific authentication mechanism, this is the authentication module. Who are you? That's identity. That's different from authorization, which is sort of the topic of this talk. But it is important because we have to kind of have this information ahead of time of who is making this request. If we don't know who you are, you're going to get 401, you're not authenticated. And then this is kind of where we're really interested in, for this talk, authorization. So what can you do? We know who you are. We know a little bit about what the request is, but what can you do? And so today in Kubernetes, most clusters are going to be using RBAC. That's kind of not quite, I don't know if it's the default, but it's baked into pretty much every cluster. It's a very common authorization policy that you're probably familiar with. You've probably written an RBAC policy. Or if you've ever installed a Helm chart, most likely it's come with an RBAC policy. Oftentimes you'll see clusters too that have an external authorizing webhook configured. That might be something that's custom. So depending on your cloud provider, they might be calling out to their own identity system or something to say, is this request allowed? And in this authorization phase, it's very limited. If you've ever written an RBAC policy, you might have noticed, oh, I can't reference labels here. I can't reference any of the fields in the object. I just can reference the API group, not even the API version, the resource, the type, the namespace potentially if that's there, or the name if it's not a create, if it's an update, right? Or a read. And then you also get some metadata about the user that comes from the authenticator. You get your username, potential groups, maybe a UID, like a unique ID across time, and then some key value extra info about the user. After authorization, you have this admission phase. So again, this is a bit of a simplified view over the previous few slides, but in admission, there's mutation and validation. So mutation, you're probably familiar, again, with webhooks, like if you're installing something like Istio or maybe even some of your own custom logic, the API server will reach out and say, I have the full request. It's fully serialized. Here's the full contents. Maybe on a create request, it'll have, here's what needs to be created. On an update, it'll have the previous and the current state. As well as all of the metadata that we had in authorization, the user information, the metadata about the request. And then Kubernetes also, in a couple releases ago, added Cell, the common expression language engine, so that you can write Cell functions and with validating admission policy in the API server and have those executed in the API server. So instead of having to serialize a request over HTTP, send it to some endpoint, hope that the endpoint responds in a reasonable amount of time and get that response back. It's quite a bit faster while giving you a lot of expressivity to govern what requests do you want to allow through. And so that's a feature that's in API server. So you get, again, this key point here is really you get the full data in admission and you do not in authorization.
Yeah. But then not for reads, which is
and that's correct. Yes, this is for mutates. So in a read request, all you get is authorization. There's no admission on reads. After your authorizer allows this request, again without the contents, it goes to storage. There's a recent feature in Kubernetes that allows a little bit of extra metadata if the user specifies it. Like if you've ever use kubectl or seen a controller select, say, pods or something by label. You can do kubectl get pods -l, key equals value or just key. That now is passed to authorization. You don't see it in RBAC because it's not in the RBAC API, but authorizers do get that information as well as some field selectors. Field selectors are, there's a few specific fields. You can look at the Kubernetes documentation for which fields are enabled in field selection, where you can specify, I want resources like secrets where type is basic auth or type is TLS.
Yeah, so we'll get to a demo of that. Yeah.
And again, so Kubernetes RBAC is really about, it's role-based access control. RBAC stands for role-based access control. Mm-hmm. So it's these rules stored in the API server. There are a few limitations here, like privilege escalation, or does have privilege escalation prevention. It does only allows, you can't do any denies. So I can't prevent, or you can't prevent requests from going through. You just can write allow rules here. And then again, as we specified before, it only operates on request metadata, not on the contents of the request itself.
Yeah.
So as you have, this is just kind of a logical diagram of the relations in RBAC. So as a subject in an RBAC, you have your subjects outside of RBAC, right? You have your service accounts, your users, your groups, and you have both role bindings and cluster role bindings in a policy. And so in this situation, you might have a user who matches both two role bindings here, right? They might be in this deploy workloads role binding because of a group membership, and then they might be specifically bound by username to a specific role binding. In this case, which one do they apply to? Well, it's an or, because it's either one that matches their request. There's a one-to-one relationship between role bindings and roles. Role bindings have a reference to a role. And then in these role rules, you have multiple rules, right? If you've ever written or seen an RBAC policy, again, you're familiar with this. You can have multiple rules in there. And so it's an or. But within that rule set, you have multiple fields. You have API group, resource, namespace, name, maybe sub-resource in there. These are all ANDed together. These all must, within this rule, these predicates must be ANDed together for this request to pass. So there's this combination of ORs and ANDs in RBAC's role bindings and cluster role bindings. And then the objects themselves are referenced basically by this metadata. So really to the left side of this slide, you can see that we really have role-based access control, truly, on these roles and role bindings. But then we kind of have these attribute-based or RBAC access controls on the rules themselves, the predicates within those rules, and then their relation to the actual objects in the system. So how do I know which RBAC roles do I need? Oftentimes, when in doubt, it's very tempting to grant too wide of permissions. Kubernetes, at this point with RBAC, it just, again, because we don't have the ability to specify these fine-grained controls in RBAC, it's more broad. And then even, again, it can be difficult to know, does this policy match what do I need to do? Okay, if I give myself admin, it just works. Maybe I'll lock it down a little bit from there. But the audit log in Kubernetes actually tells you about all the authorized and unauthorized requests. So one tool that you can use in this space is audit
Jordan's over there.
Jordan's over here. We didn't ask him ahead of time if he wants us to advertise this or not, but we did it anyway. So, but with audit to RBAC, you can actually run this tool against your audit log to infer what permissions is a particular principal, whether they're getting allowed or denied. What permissions are they trying to, or do they need? What API requests are they making, and what kind of policy do they need? Do they have too broad a policy, and can we actually write a much more specific one to the request that's actually being made? This is one of the tools kind of in your tool belt that you can use to help with RBAC and having more fine-grained policies. Also, another tool for you right now just is built into Kubernetes. There are lots of RBAC rules that you might have in your system. And if you want to know what actually can I or some other principal access, you can actually run this with kubectl. You can run kubectl auth can I. So this does a self-subject access review against on a verb and a noun. So for a verb and a resource. So can I get secrets? Can I create pods? Can I do something? To get an even bigger picture of this, there's another tool out there, Rakus, that works through this self and subject access review API and can kind of spit out a table for you of what you can do. Kubernetes has some of this built in for authorizers to say, like, what are the entry authorizers, what permissions are available. But so this tool kind of helps walk these subject access review
Basically
calls.
just issues one per in this matrix.
Yes.
Every time, like, am I allowed to do this or not?
Right. It checks what types are there and can you create them. And then another question you might ask is who has access to some resource. Cluster administrator, as if you're a cluster administrator, it's your job to ensure that sensitive resources are properly protected. And in order to audit who, and according to RBAC, this same tool, or kubectl who can by Liz Rice, can also be another tool that you can use to try to figure out who has access to what. So you can run this to sort of spit out a list here of these cluster role bindings, the subjects, and what permissions they have.
Cool. So that all you can do today already. I'm sure that, well, you can check out the tools after this talk. The slides are uploaded. And also, well, they're all open source, so I'm sure that, the maintainers of them appreciate contributions and kind of fixes and guidance there. Now we're going to look at two in SIGAUT new feature, or like enhancement proposals that are kind of up. These could then maybe help add some more granularity to the system. So a while back, I took even though I've been a contributor for quite a long time, I'm still doing my master's program at Aalto University in Finland. So I took the opportunity to, dive into this problem 2-in-1 while I needed to do the thesis. So there's a 60-page thesis if you want to kind of the deep variant of this, but the high level is presented here. So what if we could kind of get a more fine-grained feature like capabilities, what would we, for example, do? We could say that, allow Micah to only see secrets with a certain type or label or something like that. Allow, like only updates when a sensitive field is unchanged. Maybe you don't want anyone to update those kind of, something in the object. Allow someone to create an object only with a certain name. Allow a node agent that runs on some node in the cluster to only operate on, for example, pods or other auxiliary resources that is attached to that node in particular. Or allow a controller only to remove and add its own kind of finalizers. So finalizer are a delete protection mechanism in Kubernetes. Or say something like there's one KEP in SIGAUT that is about denying admin access to devices, or most likely GPUs, through the DRA feature. You might want to, for example, say that, normal users shouldn't be able to have admin access to these things. There's a feature for this already, but this kind of also encapsulates kind of the same paradigm of like, these are some ideas that you want, or mechanisms that you want to enforce. So if we look at the write request, it's basically, if we zoom into this validating admission control, as Micah said, you can kind of write it in common expression language through the GA feature in Kubernetes already, validating admission policy. So then you write these kind of, on a write request, the conditions of like, only in these certain conditions, the write should go through. Or you can do anything with gatekeeper, open policy agent or similar to guard against writes that you don't want in your system. However, the idea here is that we could integrate the authorization and admission layer even further, such that the authorizer doesn't have to kind of, in the beginning over grant, kind of say that, you can create practically any type of this resource, or anything in this resource, only to then later have another object to kind of take it away. So what if we could write this at the first stage? So we could just say that, I'm an authorizer. Micah should never be able to create a secret or list a secret when the type is not basic auth or something like that. So this works through a technique called partial evaluation. So if you have something like this that Micah or Lucas I had there should be able to create HTTP routes only when there's a certain gateway class. So that now in pseudocode, the expression would look something like this. So if I do kubectl create with this, then the partial evaluation will check that, it's Lucas, it's a create, all of that kind of stuff. So all of them are true, only up until the point where it's referenced the object. So it says that, now I don't know the object in authorization, so I cannot evaluate this request. But this is basically the condition that we can pass along with Kubernetes authorization further. So, but just to show that if an attacker or someone malicious was, trying to do the same, they would actually get a false at this point, because request user info username is not Lucas. So this policy does not apply and thus is not considered. So with this Kubernetes enhancement proposal, we extend from an authorizer saying allow, deny, or no opinion to also have a new mode conditional. And if there's a condition like this one that the gateway class name has to be development or something like that, then Kubernetes enforces it kind of later when it has data. So a condition can have, it can be any type of string, but then it has a type field where you, for example, say that this is a cell policy, this is a CEDAR policy, it's an allow policy, and so on and so forth. So in this case, actually, in the authorization phase, we get back a condition, and then we propagate it with the request to the admission phase, and then there we have the available data. So then we can kind of get a definite yes or no if this request should go through. So the authorizer is guaranteed to get the callback. So with this one, across reads and writes, we just said that the webhook, so the cell and webhook admission are only available for writes. But then with the new feature of Kubernetes, a couple of releases back, we actually can do fields and label selectors on reads as well. But now, in order to unify these with the partial evaluation, we can actually just have one interface to kind of show all of them.
Yeah, so this is kind of where I want to talk a little bit about another project that's actually newly in CNCF. So CEDAR is a authorization language. It's open source, and it's also a kind of an authorization engine. It's originally actually created by AWS, but it has a few different goals. It aims to be expressive. So we talked about expressivity, like being able to have a lot of conditions and reference a lot of things, fast, safe, and analyzable. It also maintains an encoding into decidable mathematical logic using SMT, so you can actually prove that a policy is enforceable or not. You cannot write a invalid policy. It also supports RBAC, role-based access control, relational-based access control, or RBAC, and also ABAC, this attribute-based paradigm. And as I mentioned, AWS actually just donated CEDAR to the CNCF. We opened the donation ticket in May, and then about 2 weeks ago, it was accepted as a sandbox project into CNCF. So yeah, time for demo.
Yes, so we put together a unified interface using CEDAR. And let's see.
So we have a local kind cluster, and I'll show you the policy that we have running here.
Yeah, it was in the slides.
It was in the slides, yeah.
Show in the slides, I think that's
all right.
The next one. Yes, this one. So
in this example, we want to let user Micah Hausler only read and write secrets with a type TLS. So we've got two policies. These are CEDAR policies, and I won't get into all of the syntax, but these are both permit policies. We could write forbid policies as well, but we're just really going to show permit today, where we're saying a user has to be a Kubernetes user. On the left policy, they can list or watch, and the resource type is a secret. We're going to add some conditions, not just any user. It's got to be specifically one username. And this request must have a type. If you ever looked at secrets, there's a type field. So this is the v1 of secrets and the type field. And that type field must be kubernetes.io/TLS.
Yeah, now we changed it to basic auth.
Yeah, we just changed it to basic auth for this demo. So, but in this example policy, you could see how you could to it to a specific type. And then also for create, but you'll see that there's request and stored. Stored is an admission, something that you're retrieving. Request is something you're making or creating or updating.
Let's see if the demo gods are with us.
Yes, so we'll see if the demo works. So in this write condition, we've got we're going to create a subject access review, self-subject access review, and it'll spit out.
Which is a kind of what can I do?
This is a what can I do on a specific API, and we'll get back the output here in a second. And you can see that I'm creating this in kind, and I'm doing it as Micah Hausler, so I'm setting the username, and it's responding back with a condition. It's saying this condition, yes, but when, or maybe when, the type of object is Kubernetes.io basic auth. We changed this at the last minute. And then if we say, okay, let's try to create it. So I'm going to create a secret, but I'm going to set the type to opaque, not basic auth. And we can see that gets denied. So this is the different type of secret than I
you shouldn't
specified in
have
the policy.
yeah.
I shouldn't have been able to do that. Now I'm going to set the type to basic auth. And we can see that it actually works. I was able to create a basic auth secret. And now if I, again, similarly try to get secrets unconstrained, just kubectl get secrets, I'm going to get denied because I did not have the appropriate type set in the policy or in the field selector, or as the policy dictated. Now if I actually set a field selector of type Kubernetes.io basic auth, I can actually list and get that secret back that I just created. So that's the demo.
Cool. So it actually worked. Nice.
Yes. And
yeah.
There we go.
Yeah. So
these are our backup.
Yeah. So then finally, we're going to talk about analyzability. So this, well, the condition and the framework here that we showed, it can be written with anything else in Cedar as well, but we found Cedar nice to work with in this use case, thanks to its analyzable properties. So if you have two policies, you can actually check which one is larger and which one kind of policy is smaller, and this is what we use to kind of constrain the reads to make sure that any object that could be returned is actually also authorized. And if you refactor policies, then you could check that are these policies exactly the same always. Like, you don't need unit tests. It's going to mathematically prove that, well, this policy, even though I refactored all of it, is still the same. Or if they are not, then it's going to give you a kind of a counterexample of here is a case where one policy would apply but not the other. And you can check for these kind of logical inconsistencies and similar. So it's a really powerful kind of primitive. So to conclude, where to go from here? One of the things that we can build on top is, hopefully, reference grant. So one of the kind of interesting, problems with use cases in Kubernetes is that you have references across trust domains. So for example, an HTTP route would refer to a secret in another namespace. This should, by default, not happen, or like you shouldn't be allowed to do this unless there is something in the namespace where the secret is that kind of says that, yeah, it's cool to refer to this secret from this other service full namespace. So that's an example of what we could build on top of this, among other things. But the key takeaway here is really that, well, if you're interested in this type of feature, you should join the SIG auth calls, so special interest group for everything authentication authorization in Kubernetes. There's in the Kubernetes Slack a SIG auth and SIG auth authorizers dev channel. There's bi-weekly meetings. Well, the Kubernetes enhancement proposal is up for review. Just upload it this week, and hopefully we'll get to implementation at some point as well. Try out the mentioned projects. There were a few that could be used, and get in touch with the maintainers and so on if you're interested in it. And yeah, when we have this is a kind of basic primitive. When we have this basic primitive, we hope to be able to do more exciting features such as reference grant and maybe some RBAC++ and similar that the SIG has been working on for a long time already. So yeah, that's it for today. Thank you.
Thank you.